Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. SkyTour in the night so clear, brings the universe near. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. SkyTour's bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. SkyTour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. SkyTour is bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. SkyTour is bringing the views. Every night feels brand new.
And welcome everybody to SkyTour Livestream. It's, who am I? Oh, I'm Marc D'Antonio. It's nice to meet you guys once again for this evening of beauty and wonder. And with us, of course, is Daryl. What's up, Daryl?
Hello,
Marc.
Mark. Hi, I'm Daryl.
Hey, I'm the other brother, Daryl.
Oh, God, please. No.
Never heard that before, have you?
I've heard that a million times.
No way.
And hello, everybody. Howdy, all that stuff.
Yeah. So, folks, welcome tonight, and we're going to be checking out some things that we haven't been doing regularly. We do some of the regulars. Oh, that's gorgeous. Whew. I'll tell you about this in a sec. I haven't been doing some of our other things we want to do. I've been doing regular stuff because in our database and in the app that Izabela has made for us, it encompasses several years of our data. So you can go back and check to see if there's changes from one year to the next. And indeed, we found some. Well, Izabela found some when she was doing some looks. She found what looks to be asteroids that have showed up in some of our images that we didn't know were there. Because remember, we're looking out through our solar system at the universe beyond, and we're seeing that here. Okay, this is the Eagle Nebula. All right, I'm going to back out for a second just to show you the whole view. Okay, this is the Eagle Nebula in its entirety. Okay, I'm going to give us just a little more sky brightness so you can see some of the subtle stuff in the background there that you might otherwise miss. This is a beautiful stellar nursery. It's a place where stars are being born. You can see this young hot cluster right here. And that young hot cluster has everything to do with these pillars here that we see. And these are indeed, if you might be wondering, the pillars of creation that we have seen many, many times with the Hubble Space Telescope and now the James Webb Space Telescope. So it's really, really cool. And Michael Hedrick says, hydrogen. He's right. This is hydrogen ionization by the hot young stars. And when you ionize hydrogen, it has only one electron. And when ionization is when you knock the electron off the atom, leaving a positively charged nucleus, because the proton is positively charged, +1. The electron's -1. So knock it off, it's a positive ion. But when that electron comes back in, it cascades down into the atom again. It's always going back and forth. And when it cascades into the atom, it predominantly leaves a red light behind. It makes red light as it cascades into the atom. It makes other transitions too, but predominantly it goes to a level called n = 2, the second level. And that gives us this 65, 62 angstrom or 656.2 nanometer light that we see right here. It's red hydrogen. This is what we call one of the primary colors of the universe. All right. This ionization is a sign of hot young stars, and these pillars here are something else. Now I'm going to explain it in a sec, but I'm first of all going to do a quick identification. This is called an annotation, and this is the annotation of this object. This will be saved and will show up in our server online. You can find the server here at SkyTourLive.org. See that right there? SkyTourLive.org. You go there, and as you scroll down, it'll say, take me to beautiful pictures, and you can go, and there's instructions on how to get it. As far as looking in our app, as I said last time, we're still trying to get the app online, and we're talking to the folks that we built the app with, and we're going to try and get that going. It's really tough when you can't talk to a real person. You got to do it through the internet, through emails, and I can't stand it. But that's what we're doing so far. Okay, so this again, Eagle Nebula. Let's close in now. And I want to show you this center part here, because this actually really is cool. Now you might recognize the pillars of creation. See them? There they are. Look at that. There's one here. There's one here. There's one here. And they're actually quite detailed, as you can see. Our telescope runs 25 times faster than it did natively. And this gives us the ability to capture faint objects very, very quickly. As you might notice, if we look at our screen here, I can show you that when we look, no, I don't want that, sorry. When you look at our screen here, all right, we see, for instance, here is our exposure. It's 15 seconds long. 15 seconds. This would normally take 10 minutes to capture on some telescopes of our size, but we are actually doing, like I said, 25 times faster processing, because we have reduced the size of our field tremendously, but increased the amount of pixels our camera covers. So we get this beautiful image in an extremely short time. And there's really not a whole lot of people doing this on the internet, if at all. So, and this other thing here, this is the gain. The gain is how sensitive the sensor is. The exposure is how long we expose that sensitive sensor. So this is basically what we got. But these pillars are very important because they're related to these stars. Now, how can stars, some light years away from these pillars, be related? They're related because in this nebula you can see dark spots. These dark spots are dust. Here is one in particular that's really interesting. This is actually a globule, it's called, and I'll point to it right here. I'll just surrounded there. That it's in the box. Okay. There's another one right up here if you want to look there. Okay. And there's all kinds of dark nebulae in here, and this is all dark nebulae as well. Now, what are dark nebulae? It's dust that's leftover debris from supernovae and from stars that are not high enough mass to go supernova. When they end their existence, they also slough off outer layers and dust into the interstellar medium, and we see that here. But this dust can get dense at some points and gravitationally collapse. And it's that gravitational collapse that forms things like stars. All right, hydrogen gas is the most predominant gas in the entire universe, and when it collapses with the dust, sometimes the hydrogen will collapse into a ball in the center of these clouds, and it gets hot enough, it will start fusing, and thus a star is born. Okay, and so, but the dark dust itself also has gravity. These little tiny particles of dust, usually made of carbon and silicon, will collapse and gravitationally collapse. So at the ends of these stalks here, these are the denser parts of these things right here. These are the dense areas. And so this stellar wind, this copious, powerful radiative winds coming from these stars, is pushing away all the material around here and in between here and between these fingery looking things. And it pushes the stuff away. And as it pushes the stuff away, the denser stuff remains behind and protects the stuff behind it. So over time, we get a stalk. They're very, very common in the universe. And when we look at other things and other phenomena, other objects, Daryl and I have both pointed out that we see these stalks that are in play. And they come from this stellar erosion caused by the stellar wind. So there's a little mini lecture. Done with that for now. Let's just now enjoy the beauty of this object.
If you look at the central stalk, it looks like you see a couple of stars
Right here?
coming to life. And yes, right there.
Let's zoom in on those.
Forget it. There may be one in the tip of the eagle's beak too.
There's one
That's-
right there.
That's the eagle's body. His nose is pointing toward those stars at the upper right. You see the wing going above and to the lower left, and the little thing to the lower right is his foot.
This?
That's no.
I don't know. Let's see this here.
Yes, that's the eagle's foot.
Man, that's like a second grader's drawing of an eagle. I've never been able to see the eagle in this, literally, and I'm good at pattern matching. I don't know how they saw an eagle here. You know?
Somebody did. I see it.
I know. Yeah.
And if you back out a little bit, there's another neat thing higher up on the left.
Oh, yeah, that's up here, right?
Yeah.
I'll move it over. This right here.
That's called the fairy.
Right here.
It always looks like a hood ornament or a Oscar award or something to me.
It looks like the front end of a Jaguar. It's got bugs on it. Yeah. That's cool.
But you notice they all point more or less toward those bright stars in the cluster,
That's right.
because that's where the radiation pressure is coming from.
That's correct. As Daryl says, you see this long stalk? This is a dense area. And I'm not sure if that star in there formed as a result of that, or if it's in the foreground. It could also be in the background and just bright. But we could figure that out. But you'll see that we have lots of detail in these pillars. This is something that was not available to us with the previous camera we used. And that was because it didn't have enough pixels in the square image to capture the many details. Now we have almost twice as many, and that's pretty cool. And that gives us the ability to see this detail.
Michael Hedrick, yes, it happens, and the comet Neowise may not be the same comet Neowise as the one you're thinking of. Just like you see Atlas there and others, those are like search programs, and they all get that appellation. But speaking of comets, I meant to mention that you may remember Tsu-Chin Shan Atlas.
That's right.
C2023A3, I think it is. It's possibly going to put on quite a show in a few weeks.
Yeah, we're going to
We
see
kind of watched it down into the sunset, and it's going to move to the morning sky and pop up before sunrise for a while. I think at that time it may be down in the southern sky, but then it's going to drop back into the sunrise and then pop back up into the evening sky again around the time it comes to perihelion, closest to the sun, and then passes closest to Earth. And it may turn into like a magnitude -3 comet, which is very, very bright. They're saying it could be brighter than Hale-Bopp was back in '97.
Excellent.
Which was a -1.86, if I remember right. So we may be in for a show here in a few weeks.
Hope so. I want to say hi to Michael Hedrick, who was here first. Yoo-hoo. Okay. Suzette Bavier, how are you? Nice to see you. Sam S. is with us. Red Angel, nice to see you as well. And we have, let's go down the list here. Michael Galea, that's cool. Hey, Mike, how are you? I've seen you coming in recently. That's cool. Donald Kunzer's with us. Desert Dweller's with us. How you doing, man? And let's see, Judy M is with us. Nice to see you, Judy. Thank you for coming. And let's go further down. Old School. Hey, man, what's going on? Nice to see you as well. And Fantasy is with us. Nice to see you, Fantasy. Asher, what's going on, brother? Nice to see you as well. So yeah, so you guys are the ones that are chatting, but there's more people watching. So let's keep up this momentum. You know. Okay, so I had started this exposure early, just to try and get up to around 100 exposures before we actually moved on to the next object. But that's given us time to have some of the objects out in the northeast get a little higher in the sky so we can start to see those as well. It's really very, very cool evening, and it's beautiful out there. It's actually 35 Celsius out there right now. in our telescope.
Mark, your sound started breaking up something awful.
Well, maybe that's to you. I got to find out if it's happening online.
I've heard this happen before. Can you guys hear Mark okay?
We'll
He's busting up so bad for me, I can't make out what he's saying. And can you hear me okay?
All right. Yeah, it's okay. So it's actually at your end. It could be that it's related to the microphone. Yeah, they say both sound
like you're
fine.
speaking a foreign language, Mark.
No, I am not. So we're good on the broadcast. That's all that really matters. I'd love for you to hear me, Daryl, though, however. Be kind of important. I'm going to try something, guys, while I'm here. Since we're here, I'm going to increase the sharpness quotient here. Try and catch more data. Look at that.
Boom. Did you hear the lightning?
I did hear that. I heard the thunder. That's really cool. Yeah, see, I increased the sharpening, and you can see inside the pillars, you can see stars in here. These stars were not available to us with the previous camera either. This is really cool. Wow. Okay, we're at 101. I'll save it now. Save it exactly as seen. Okay, that's good. All right. So those are the pillars of creation, the Eagle Nebula. Let's just zoom out to show you the entire nebula, do some final processing before we move on, and then we will...
I think Red Angel asked how old is the pillars of creation? How old is the nebula? I don't know offhand. I mean, you're probably talking millions of years.
Yeah, the stars are several million years old anyway. If they're young and hot, we can move this up just to kind of show you a little bit more about what's going on. And now you see more details in here. And to see what's really going on, I'm gonna do this one hit pump up of all the background here, so you can see. Now you can see all the rest of the nebula that are actually in here. This is on our imagery, and you can also see satellite trails from Starlink that have come through. I have to say, for all the problems that Starlink causes us, I gotta say, I'm impressed because our service has improved by about 500%. And it used to be that Starlink would hesitate and go out sometimes, and I have to say, okay, we got to wait for about 30 seconds or whatever. I haven't had to do that for like, I don't know, 4 months now, so I'm cautiously optimistic. Thank you, Daryl, for putting the link out there for the images. All right, we'll take, save one more and go. And by the way, this right now, this image, I say it's being saved. Here's the image. I'm bringing it up right now. This is the image that goes up to the server. This image is available to you. You can go and download it right away and use it and take it and use it. All right, so these are free images that we give to you. All right, now when we process them, we get rid of digital noise. We process for proper colors. They're close now, but it just gets better and better. And if you join our Patreon, which would be great, you know, our Patreon is something that helps keeps us going, because right now, you know, we are trying very hard to you know, make some goals. We are setting up that second telescope in Benson, Arizona, and I have to take care of getting that structure built, you know. So if you go here, if you feel like it, you can join our Patreon. The Patreon menu is in there as well, but you can also just, if you want to donate, you can donate to us as well. Now, for the record, I'm not making a cent on this, okay? This is all, everything is donated for the last 4 years has been going in to furthering the experience for everybody who's watching, because I think that's the most important thing, you know. As an astronomer, you know, that's what I got my degree in, as I've told you. It's, to me, it's about the passion of looking at the night sky and understanding what we're seeing, and that's what this is all about. We'll do one more save, because we can. All right, save exactly as seen. All right, now we're going to come back and go into what we call low light mode. All right, and low light mode you'll see in a second. All right, this is low light mode, and we'll increase the size here. All right, so that's what the Eagle looks like in a small to moderate telescope. This is what you might see with the Eagle when you look at it. You might catch a little bit more detail than this, but it's going to look kind of like this to you.
Dark sky, you can see the Eagle pretty easily.
Yeah, as long as you're in a dark sky. We're in a very dark sky here, but let me do one more that's right near it, okay, which I think is really cool. And it is right here, because we're so close. We'll just image this, do a few images, not the same number. But this one is called the Omega Nebula, or the Checkmark Nebula, or the Swan Nebula, or the Horseshoe Nebula. Why so many names? I don't know. But it's pretty cool. Another stellar nursery, similar but different.
Or the Duck Decoy Nebula.
Oh, yeah, the Duck Decoy. If you rotate it upside down, it looks like the duck's head and beak and the body of the duck here. Yeah, let's just move it a little bit west and then go a little bit south. There we go.
Maybe they should call it the Duck Dynasty Nebula.
Yeah, I don't see any glasses, like the big Coke bottle glasses. Okay. All right, this we'll do another. We'll do in this case we'll do 25 seconds because this is the nebula, but you got to see what's out here. It's really incredible how much is really here. So we're gonna come out of low light mode on this and go into our live stacking mode, and it will have the buffer of the last image. You'll see the Eagle Nebula one more time. There it is. And we'll clear it. It's up on the server. Now you'll notice these numbers. These numbers show that our secondary telescope, which you see right there, right there, okay, is guiding. And let me move this down a little bit here. Just take this down a little bit into me so you can see that a little better. There we go. Look at that. So much going on in this image. I'm zoomed in a little bit. Now what's cool is this is a stellar nursery, and you have this hydrogen emission I was telling you about, where the ionized hydrogen, the electrons recombine with the nucleus and form an atom again briefly. As they do, they give off that red light. But you'll also notice here and here you have this very different coloring. It's almost a blue. Daryl's on his Harley again.
Sorry, I got the back door open.
That's fine. You got that here and you got it here. Okay, you see those little things there? And it actually kind of extends into here a little bit, you know. But those areas are areas where we have a slightly different type of nebula. Because remember, there's gas here and there's dust here. And the gas affects the nebula one way, and the dust affects the nebula another way. And a few days ago, we did a Trifid Nebula, and it has a red three-lobed nebula, which is an emission nebula, and then above it and surrounding it was a bluish nebula. We're seeing the same thing here. This is the dust that's out here. Okay, this is all dust, by the way. This is all dust in here. This is all dark stuff. Okay, but the dust right now here is actually taking the blue light from the hotter stars that are in here somewhere and scattering it, just like the molecules and atoms in our atmosphere scatter the sunlight's blue light, making the sky blue. So we're getting a blue sky effect for the same exact reason out here in this nebula. So it's kind of cool how it's all related, yet light years away. Yet we're seeing the same actual process. It's called Rayleigh scattering. It's a particular scattering effect, which is neat. So we've got 6 exposures here, and what I'll do is I'll color correct to see if we can bring out a little more detail. There we go. And let's see where it wants to process. It's going to pull down the brightness a little bit, enhance this. That's looking good. And I'm going to just, this is the black level, and this white curve is the average of our red, green, and blue curves. Okay? And when you color correct, the curves are all lined under each other. And now what I'm doing is I'm moving this black level to just to the left of the curve. If you go to the right of the curve, you start losing detail. See, watch. Okay, see how it goes away? But if you come back, the further you go, you end up getting to a point where you're just to the left of the curve, and now you've got the maximum amount of data with the maximum darkness in the sky. And this curve pushes that faint data and makes it brighter. The closer you bring this line, the brighter that faint stuff gets. However, it can also blow out the center. So now you see more data and more nebulae out here, but we lose the detail in the center. So that's why we don't typically do that. We typically leave it right like about here.
What is the yellow line?
Which one? This one? That one?
Yeah.
Oh, okay. That yellow line represents the actual data that we're actually pulling in. So we're pulling in data that's here all the way to here. And so that means data from here all the way to here. it's kind of showing you where that data starts along this line. So,
is there any significance to the place where the lines are crossing?
here, no, not really.
Okay.
If I bring this to that location, you see the line moves with it.
Fantasy asks, why is it parabolic and not linear?
Why is what parabolic? This here?
The curve, I guess, yeah.
Well, that's actually not parabolic. It's actually it's a Gaussian curve, and the Gaussian curve also trails off, all right, because we have other data, so it adds on. So it's sort of see where it goes? It goes all the way down here. So it trails off. You're actually looking at the maximum amount of data is here at the very top. Okay, and see, now you can see we didn't lose any faint detail. Okay, but we have that maximum darkness. This data is trailing off, and if we go this way, you'll notice that we're actually now including some of the fainter data, and we go into noise down here. And when we get all the way down here, you'll notice that the nebula looks really, really good. All right, but we're losing a lot of this other data because we pulled this entire curve way down into the weeds, and we don't want to do that. We want to keep the data out of the weeds. So where you see it get all scrunchy like this, that's kind of where it starts getting into the weeds. So if we come back to just about here, okay, that's just about the best we're going to get, and maybe a little more. So right here is where it starts to come out of the weeds. And sure enough, this is the maximum brightness, maximum detail, maximum background detail that we can see in here at this point. But we'll use these lines to actually do processing on the fly so we can see things. Like, let's say we wanted to see the details inside this nebula. We've got 15 shots done, right? Now, if I'm actually pushing, which is what this is called when you do this, if I push this, well, that's all blown out. However, if I take this down a bit, back down a little more, all right, now the data becomes clearer and you can see what's going on in there. And this represents what's called the dynamic range of our image. So we can take an image and see all the way into the core of like a globular cluster or a nebula like this, and see all this detail at the same time as being able to also process it to show us all the detail that's outside and out here. So that's the beauty of these cameras. They have this massive range that they acquire. And unlike a regular film camera, if you overexpose the center, the data's gone. But as you can see, we can overexpose the center, and it looks like the data's gone, right? And it looks like all that detail in there is gone. But when we pull it down, when we actually pull this like this, we'll see that the data comes back. That's preserved. So this gives us a lot of flexibility when we process. We can process for the center, we can process for the outside, do a mixture of both. And many of our final processed images will show a balance where we've processed it in this way, so you can see the best balance. Those are fantastic questions about how this all works.
I see a big monster eating the duck.
This one?
No. If you see the duck, just immediately to the duck's left, there's a big dark area. That looks like the mouth. And the red bally thing above the duck is its nose, and maybe the two eyes above that.
These being the eyes?
No.
I don't know. See, the duck's
the big red thing right there.
Yeah, this here.
That's the nose.
Or this.
The red ball thing to the upper left of where you are.
That.
The big red thing, upper, right there.
Okay.
That's the nose, the mouth below it,
right
with
here.
the duck sticking out of its mouth.
And here's the duck.
And then above that red thing, there's like two darker hollows, and say those are the eyes. Isabella's here. Hello, Izabela.
Hi, Izabela. And good morning to you, Izabela. Yeah. You know, Isabella's in Bulgaria, so when she comes on with us, she's really pushing it because, for her, it's still early in her morning, so she's getting up really early to get to join us here. And for people in Australia, well, it's a little different because they're into their day already. I was talking to someone in New Zealand yesterday, and the conversation lasted about 2.5 hours. And we were discussing television stuff that I'm working on with her. But right now, they're they're in the middle of their day, and it's really difficult to actually get on the phone because you're either talking really late in the night for me or really late in the night for her when we're trying to talk about this stuff. So it's really hard to coordinate a project. It really is. We'll go to 25 on this. Look at that. That's pretty, isn't it? Now, here's the thing. This nebula, I've always it's been like, I wasn't too excited about it. But then I noticed that once we converted the telescope to be much faster, there is so much more to this nebula than meets the eye. And if we pull this in a little bit, you can see that this other stuff is out here. I never knew that. In our previous iteration, we only saw this. We never saw any of this. Remember that, Daryl? Oh, sorry. I have a keystroke that talks about the objects, and that was not it. So that's what's interesting about this. Hey, Kevin O'Neill, how you doing?
Oh, I don't know. I mean, I think you're catching more now than you were, but
For sure.
Surely we saw some of that before.
If so, I don't remember it. I'll be fair. I don't remember.
We'd have to go back and look at the app.
Yeah. Again, remember, everybody, if you wanna see all this imagery and take down copies for yourself, right here, SkyTourLive.org. We are a non-profit organization. Donations welcome if you can do it. and as I said, I don't make any money on this. This is all a labor of passion and love. There's a possibility that we're going to relocate this telescope, by the way, and that's not coming to fruition at this point. But if we relocate this telescope, we're looking at some sites that are literally, this is a dark site, but we're looking at sites that are twice as dark as this. So there's some in New Mexico, there's some in south of Tucson that we're looking at, and that might just be a whole nother telescope system for all I know. And we're looking at potentially getting larger aperture if we can ever do it. Right now we can't do it, but if we could, that's where we're going to do it. Way down there. Thank you, Izabela, for putting up the server folder. Okay, one more to make it 30, and then we'll save the Omega Nebula. It's coming in right about now. Boom, there it is, save. And right now, we don't have any wind to deal with out there. We're actually doing pretty good. So we're good. So I'm going to take us back into our low light mode from our deep sky mode. It's kind of like a finder mode, right? We can actually see the sky. It's kind of like a night vision mode. All right, and we'll bring up our other linked system that allows us to look for things in the sky. And let's head up. Last night we did LDN, or the night before rather, we did LDN 673.
Yes.
Which was a dark nebula. It's up on the server. It looks pretty good. Yeah, and I'm going to move up. Look, I'm moving up the Milky Way. You can see it here. There's Altair, which is in the Eagle, Aquila the Eagle. There's the Eagle, right there. Well, you
The Sagitta, that's the arrow, as you can see.
Yeah, I was like trying to back out here to show this. What am I doing? Here we go. Okay. Oh, duh. Okay, there we go. There's the Eagle right there. There's Vulpecula, the little fox. Sagitta, the eagle. Sorry, the arrow, as Daryl said. And in Vulpecula, there's a beautiful planetary nebula that we love to look at here. And I'm kind of aligned on it right now. I'm going to go to it. It's called the Dumbbell Nebula. And when I go up there, the telescope's going to move quite a lot, as you can see. All right, and we also have a satellite coming through the view that is now gone. But as we come here, there is the Dumbbell Nebula. And the Dumbbell Nebula is a beautiful planetary nebula. And a planetary nebula is a nebula that is the remains of a star that's not massive enough to go supernova. And so it just, as it becomes a red giant, it starts to do what's called thermal pulsing, as you'll grow and shrink, and every time it does that, it sloughs off an outer layer of itself. So all the stuff you see that's lit up there, this is the material that used to be in the envelope of the star that sits around the core. Only the core is fusing hydrogen into helium and, and helium into carbon and so forth for stars like this, because they don't fuse much more than that because they're not massive enough. But this particular object is the remains of one such star, slightly more massive than the sun, and it actually sloughed off its layers. The bluish green, that's oxygen, and the red is hydrogen, our old friend hydrogen. And what I'll do now is I will start an exposure of this. I'm going to make this a 15-second exposure because this is a very bright object, and we can capture. Okay, I'll make it 20 seconds. We can capture a lot of the detail in it with a shorter exposure. So let's go start our come out of low light mode and go into our deep sky mode, and we'll see the previous image that we took. There it is, the Omega Nebula. And we'll clear that. That's beautiful. Oof. And now you'll notice one thing. This nebula is more compact than the other one. Not as extensive at all. And the reason is because it originated from just that one star that finished its existence. And there it is. Oh, look at that ring. Look at that line of stars right there. That's cool. That's really neat. I didn't ever see that before. So now we'll zoom in. Now we only have one object in here right now, but one stack object. But we're gonna color correct, and you'll notice that it's gonna get a lot better. And this is gonna come back this way. Take the dark
already
level.
See the white dwarf in the middle?
Yes, you can. That's right. And it'll get more clear. That object right there that you see in the middle, as Daryl pointed out, is the white dwarf. That's the remains of a star that's not massive enough to go supernova. We're going to pull this way down so you can see that with more clarity. Okay. I'm going to go even more than that. And we'll bring it up as we get more exposures. Bring it way down into the weeds. Okay, look at that. So, that white dwarf is, oh gosh, how far is this? Is it 2,000, 2,500, maybe light years?
I don't remember. Give me a second, I'll find out.
Hey, look it up, thanks. And that that's the remains. That's just the core. Now, this particular white dwarf is actually about the size of about Jupiter's diameter, maybe a little bigger. That's the core size, but it's a white dwarf star. Now, we're looking at something that's many light years away, and something the size just a little bigger than Jupiter can be seen. That's how intensely bright it is.
Jupiter? I thought it was like the size of Manhattan Island.
No,
It's 1,360 light years away.
the core of the star, okay, no, the white dwarf is the size of the Earth, but the core of the star, when it was a star, was about the size of Jupiter, and then it shrinks way down to like the size of Earth, all right, and then it expels all that debris on its outside. So I'm sorry if I wasn't clear about that.
The 3 Mile thing, or Manhattan Island. I think I was thinking of neutron.
Yeah.
On the stars.
Yeah. That's cool. So now we can see now very clearly this white dwarf. Let me zoom in a little. Look at that. You'll notice also something about this white dwarf. It's decidedly or markedly blue, isn't it? That's because it's very hot. It's like 35,000 or 40,000 Kelvin, which is extremely, extremely hot, okay? And that means that it's going to be hot and blue as small as it is. And because it's so hot, so small, so bright, we can see it from, 1,200 or 1,500 light years away, whatever the actual distance to it is. Now, in telescopes, you can see this shape of the dumbbell like this, and when you're looking at it with your eye. In a smaller telescope, it might look more like, I'm thinking about, maybe just a little further in. With a small scope, it might look like that. Okay, it's a very bright, it's called planetary, but it's a very bright planetary. But if you're taking a photo of it, you'll always get something at least this bright. And if we go out just a little more, we only have 11 images stacked right now, but if we come out just a little bit more, all right, you can see, and I'll bring this in. Actually, I'll just put it where it wants to go, and it'll actually make it brighter. Probably too bright.
There's some faint outer shells to the left and the right and the upper right.
Yeah, that's what I was getting at. So you'll see the blue colors out here. Okay, you'll see blue color out here. You'll see wispy structure in here. And we'll see more of that as we capture more images. And I will mark this as the Dumbbell Nebula. It's called the Dumbbell for obvious reasons. It looks like it. And it's a PN, a planetary nebula. Hey, awesome hippopotamus, how are you? I don't know. He says, Marc Scope puts my sea star to shame. No, you know what? The sea star is a good scope for people who want to check things out. It was never built to be something that could show you Hubble quality images. Neither's mine. But it can show you some really cool images on its own, especially of things that aren't, terribly faint, and then the exposures can show you some good detail. But the sea star was a cool invention. It's kind of low resolution, that's all.
If you look closely from the white dwarf in the center, you can maybe see kind of a cloudy, hazy line sticking over to about 10 o'clock, and again, a brighter one sticking down to about 4 o'clock. And where those are hitting that outer shell, that's where you see the brightest red. We've talked about this before, that I suspect the white dwarf is precessing as it spins on its axis. That is, its axis itself is kind of describing a conical arc inside the nebula. It's
doing this. That's something we've talked about a lot. I'll show you the line Daryl's talking about. It's this line through the center of the white dwarf. Okay? And now, here's the thing. The north and south poles of the star were like here. Okay? And that is north and south roughly. So we're seeing this bright line here of material and this bright line here of material. So it also, if you notice, it comes to here and then stops, right? And then the same thing here. It comes to here and stops. It's like a little arc. So if you imagine something spinning around like this and precessing and doing this kind of wobble like the Earth does on its axis, okay? We have precession on our axis on the Earth, 26,000 years it takes to go around. Well, a star goes faster. So it'll naturally describe that shape in a shorter time. And so we see that it goes here, and then, at one other point it was here, okay? At another point it was here. And so it looks like it's going and wobbling back and forth. Now, is it really doing that? I don't know. But from just looking at this, it appears that that's what I'm looking at. So it'll be interesting to see. And we'll look for some research on that at some point. Yeah, I won't pollute that here with you. Alright, so we have 21 shots of the Dumbbell Nebula. We see the faint outer reaches. I'm going to actually bring this down to the point where we can still see those faint objects, but by dropping this down, we're going to see stars inside clearer. And we'll also be able to see less noise in the image. Yeah, that's good. Look at that. That's one of the best images we've captured. But then again, look where the telescope's pointing, guys. It's pointing straight up, almost. That means that we're looking through the least amount of atmosphere to see this object.
C and D, I'm sure Marc will correct me if I'm wrong. What we're seeing isn't really that big. You may be talking on the order of 1 to 3 light years across. The brightly illuminated part of the nebula, that's sort of how far the radiation coming from the white dwarf is still strong enough to excite the atoms and cause the ionized light.
Yeah.
And planetaries are typically within a size range like that.
Yeah, if you look, you'll see there seems to be a limit, right? Everything is within this circle, basically. And so you see this faint area here, you see this faint area here. So that white dwarf, being as hot as it is, and this nebula only being about 12 to 1,400 light years away, means that the white dwarf's ionization potential extends out a couple light years. So we're looking at stuff out here that might be 2 light years out, maybe 2.5. If we know the size, if we know the distance, we could calculate all that and figure it out, because I wrote a program to do that, and we could figure it all out. If you want to dive into those weeds, I love diving into those weeds, but I don't do it in the public streams. I do it in private, and then share it on Facebook and stuff like that. But this is neat, this is kind of the ionization potential, an ionization radius, or diameter rather, of this object. It's pretty neat.
I wonder what makes that distinct line around it. It's shaped like an eye.
This? That thing?
No.
Or this?
The line around the outside that has an eye shape to it.
Like a human eye, not a letter I.
Kind of like a double teardrop.
Okay, this.
That distinct bluish line, except where it's red.
Yeah.
Seems to be a distinct shell in there.
Yeah, typically, if there's nothing around the planetary nebula for dust or gas, if it's a relatively quiet location, so to speak, in the interstellar medium, these things expand in a spherical direction. However, depending on things like the rotation of the stars, some stars rapidly rotate, some stars are slow rotators. Stars like this might have been rapid rotators, possibly, so that this is the equatorial region here, and it whips out this material to the east and west, effectively, not the north and the south, but the north and the south is the overall expansion of the shell that you're seeing. And if it wasn't precessing, perhaps this would just be an even spherical shell of stuff. Remember, it's this way, it's in front of you, it's behind you, and it's all on the sides. So we're seeing it in 2D, but it's actually a three-dimensional object. And there's this particular shape where it looks like it's got these parts being flung out on either side. We call these bipolar planetary nebulae. They're bipolar, meaning that they have these distinctive lobes that are generated. And again, it has to do with the characteristics of the star, the progenitor that made it. White dwarfs, however, are very much understood. This is probably a carbon-oxygen white dwarf in the middle here. You also have magnesium neon white dwarfs, but this is probably carbon-oxygen for the lower mass. And so this star, perhaps, we know that it has an ionization radius of a certain amount. Okay, and more than that, we know it's not going to ionize gas out there. But these are very hard to tell the distance to, because there's so many factors determining the size of a planetary nebula that we have to really carefully map out the extent of the ionization to kind of get a rough idea of how far away it is, knowing the temperature of this white dwarf. So we could say, okay, because it's a white dwarf, it's going to ionize out to, say, 1.5 light years in this direction, say, or 1 light year. So we have to look for ionized material, and if we don't see it, it could mean it's just not there yet, because this thing is expanding. It's an expanding shell. We're always seeing something in motion. So we don't know how far out it's gotten, and that makes it harder as well.
Mark, on your histogram, can you scoot the yellow dotted line over to the right some?
This one?
Yes.
To lower the brightness in the center?
Yeah, make the whole thing darker.
Yeah.
When you see it here, I'm trying to cut back on the stuff out to the left and the right.
Yeah.
Perhaps you'll get an idea seeing the red part at the top and the bottom, and then the shallow indentures to the left and the right toward the inside. See why they call it the apple core sometimes.
That's the waist. Like that.
See an apple core?
Yeah, right here.
Okay, thank you.
Yeah, sure. That's neat. This is a really beautiful shot. It's and our full width half maximum filter is in full effect, and it's working great. I can actually lower this. We didn't have to worry about it. And what does that do? It makes sure that if the stars get oblong in any way, the image is rejected. So we have a perfect guided image right now, and that's actually pretty cool. Yeah, so okay.
Curtis Horn is here.
I was just gonna say, is Curtis here? Hi, Curtis. Hey, yeah, shooting arrows at apples tonight. Yeah, that's right. That's right. Yeah, I'm William Tell. Look. Okay, so 42 images. That's a lot for a dumbbell. It's faint, but I'm sorry, it's not faint. It's actually very bright. So we'll save it like that. And let's save it exactly as seen. All right. Now let's go back into low light mode, and this will be up on the server in just about 30 seconds. And so you will be able to see everything it's doing in just a moment of time. All right, and let's go into low light. Here we go. Okay, and let's back out a little bit. And what we're doing is we're trying to image some of these things, waiting for the constellation Cepheus to come up a little higher into the sky. But while we're here, I would like to take us to something we haven't imaged yet, and that is, let's go to Satyr and do a quick shot of the Gamma Cygni Nebula. This is a nebula further up in Cygnus the Swan, and Satyr is the central star, and then just the Northern Cross or the Swan. And there it is, right there. That's Satyr, and that's actually well placed because what we want to see is right here. Okay, there we go. So that said, we're gonna make this a 25-second exposure. Now that's fully dark. Another thing we have in addition is we have our AllSky camera, which is here. This shows you our night sky right now. This is a live view of our night sky. And you can see the summer Milky Way right there. Here is the beautiful rift in the Milky Way, the dark rift there. Cygnus, where we are now, is up here. And if we turn on our constellations, you can see there's Deneb right there. Okay, and we're right here. We're in. They're off just a little bit, but that's okay.
Yeah, I was about to say.
Yeah, no, it's a little bit off, but that's okay. Yeah, but we have Deneb here and the North American Nebula that we imaged before, and then we have Satyr right here. All right, and then
Alberio down at the bottom.
Then we have Alberio right down. You can see right here. Right here's Alberio. We have our summer triangle, which we've talked about before. The summer triangle of stars, which are, Deneb, and we have Deneb right here. Okay, which is there. We have Vega in the constellation Lyra, and then we have Altair right here. And then it goes back to Deneb. And so now what this tells us is this is our summer triangle that we always look for. Really pretty. And that summer triangle is how we basically say it's heralding the arrival of summer. And now it's September, and we still see it. Okay, and it'll be there for another month or more.
Oh, more than that.
Yeah, a couple months. But, in prime viewing, so.
It'll drop down into the western sky as we, near winter time. Actually, I've not imaged, but looked at Vega and the Ring Nebula on Christmas night before.
Yeah.
It's low in the west then, but you can still see it.
Yep.
And you'll see the Northern Cross standing upright in the west at that time.
Yep. I want to say hi to Cosmic Ray, who's here. I want to say hi to Emad, who's with us. And Marco's with us. How you doing? Nice to see you. All right. So let's go back now. Let's come out of this AllSky view. We had a satellite going on the right side there. All right, so right now, this Satyr, what we're going to do is we're going to take our 25-second shot, and we're going to go into our deep sky mode and see what's hiding behind these stars, behind this right here. This is a very dark sky sight we have. We have a little bit of light from Phoenix, 75 to 80 miles to our east. That's what the AllSky showed us. There's the remains of the beautiful Dumbbell Nebula that we had, which is up on the server by now. And while we're waiting for this shot, I'll show you once again. There's that's actually a plane, sorry. Okay, this is a 15-second shot. Here is the lights of Phoenix. You cannot see them with your eye, but with a sensitive camera, you can see them. Okay. Our images just come in. Let's go check it out. Wow. Here we go. So this is the Gamma Cygni Nebula. Gamma Cygni, we mark the stars since antiquity using the Greek alphabet, alpha being the brightest. So Alpha Lyra is Vega, one of the summer triangle stars. Alpha Cygni is Deneb, Alpha Aquila, Aquila the Eagle, is Altair. So here you see this beautiful star. This is Gamma, so Alpha, Beta, Gamma. The third brightest star in Cygnus is this one. And what we'll do now is we'll actually color correct, and then we will go and do some initial processing to start to show some details. Yeah, look at that. This is a beautiful diffuse nebula, and I can pull a little more detail out by pushing, bringing this mid-level in more. Color correct a little more here. And now, so what you're seeing is not a red nebula here and a red nebula here. This is all one big red nebula. But wait, Mark, this is dark here. Yeah, this is dark dust between us and the nebula behind. That dark dust is here, all right? And the nebula is back here. And we're seeing this dark dust bisect the nebula, which is behind it. So, again, the universe is in 3D, don't forget. All right. So we'll let a few of these come in and have some fun. What's with the doodah?
Oh, nothing.
Okay, so now we'll bring this up here, make it a little darker. And let's back out in Gamma Cygni a little bit, just to show you a little more of the extent. Look at how big that is. See, so you see that now you can see this black, dusty nebula that is bisecting it. See that? Hey Waldo, what's up?
Donald Kunder asks, Mark, are all the nebula and Cygnus from the same nova? I'm going to step on your toes and say no.
You don't have to worry about that, because you're right.
When we look up towards Cygnus, we're looking over toward the next spiral arm of the galaxy. And it's a very large area in the constellation of Cygnus. There's plenty of room for many novas, many supernovas, black holes, you name it. There's a lot of stuff up in Cygnus.
Yeah, and all this dust that we're talking about here, that Daryl's referring to, this dust did not come all from just one supernova. It came from many supernovae. There's a lot of dust out there, you know. So even here in this one frame, we're seeing the results of countless supernovae, perhaps 1,000, perhaps 100,000, perhaps 1,000,000, you know, even more. So there are lots of contributors to the dust we see all throughout the universe. But it all builds up, and it's the stars are all orbiting the galaxy, so the dust itself that is made from these supernovae is also orbiting the galaxy. It's sort of like a big mixing pot, isn't it?
As we move north, the cosmic terrain, so to speak, kind of changes. And when we get to Cepheus, I hope to point some things out that are kind of characteristic of the area.
Yeah.
Cross that bridge when we get to it.
Yeah. Cosmic Ray asks, how to tell the dust from the black sky? Excellent question. Okay. Depends where we're looking. If we're looking toward booties, for instance, there's a dark void there. And by doing spectral analysis and radio telescope examinations, we can tell what's in there. We can see, for instance, using infrared as well from James Webb and from Hubble, we can map the somewhat warm dust that we can see in the sky. In this region, this dust stands out like a sore thumb in the infrared. And then as we leave this region and move to an area that doesn't have a lot of dust off the galactic disk, we won't see that same infrared signature. You know, Spitzer was really good at mapping out the dust in the galaxy in that way. So it's really an infrared study, a radio telescope study, because neutral hydrogen in the dark emptiness of space also gives off a signal that we can look at.
When you're looking along the plane of the Milky Way, you're guaranteed anything black you see like this, that's dust.
Along the Milky Way, yeah, exactly right. Yeah. Yep.
Marc pointed out the Great Rift earlier on the AllSky cam, and
I'll go back to it if you want.
this is all,
Right here.
it's all dust.
And then in Cygnus has its own rift here. Okay. And this is the rift here in the Sagittarius arm of the galaxy. And it's hard to think of this as not the same arm of the galaxy, but it's true. We're looking here at the Sagittarius arm, and up here we're looking at a different arm because we're shifting our view. Here we're looking toward the center of the galaxy. Here we're actually looking away from the center of the galaxy. And then up here, when we get to Cassiopeia later on, okay, we're looking at yet another arm of the galaxy. So we're seeing different layers and distances in our own galaxy. This section here is about 25,000 to 30,000 light years away from us, this central part of the galaxy. Maybe a little closer because we can't see all the way to the center of the galaxy. And this here can actually be farther away. When we come here, it might be a little closer actually. And then when we go to Orion, we're looking at among the closest regions to us, because that's a spur, as they say, the Orion spur. That data is changing too, but that's closest to us, and it's about 1,500 light years away that we're looking at there. And so that's another part of a galactic arm out there that we're looking at, and it's the Orion spur within which we sort of reside. So there's so much three-dimensionality to this universe. Look at this, guys. Look at that. I do have to say to everybody, this halo you see around Sadr, that's SADR, that's how you spell it. This is an artifact of our telescope, because our camera is on the front end of the telescope, and the camera is much faster, the telescope's much faster photographically. So bright objects will create these halos, and we can get rid of those post-processing. Okay, there's 20. We'll save that now. Nope, not yet. I gotta.
A while ago, you mentioned how stars have Greek letters for their designations. At the same time, though, many stars, that's not the scientific. The scientific designations start with the Greek letters. Common names of a lot of the stars, though, Sadr there, for instance, the names are Arabic.
Yes.
We've talked about this before, and Fantasy may chime in. Sadr is the central star of the Northern Cross. It's also where the wings join the body in the swan. And Sadr means chest or breast, like it's the breast of the swan.
Yeah, that's all good observational stuff. Now, in the song you heard at the beginning, I talk about I have a quote in there that pays homage to Daryl's ever interesting contribution to SkyTour, when he talks about telling stories of the stars and that's for him. I put that in there because I wanted to point out the value of that to our SkyTour live stream. This is gorgeous. And let's zoom in a little bit. You can see as we zoom in here, let me just zoom into this. Look at that. You see now, you see how this is black dust in front of this little tongue of nebula, and then there's a darker, more dense dust in here. You can see through a little bit of it here to what's behind, but you can see that that is a structure that's over this brighter nebula behind it. This bright nebula behind it. Yeah, so it's pretty cool.
And that black dust is closer to us than the illuminated parts are.
Yeah, that's what I was just saying. And then, in some cases, there are holes in the nebulae, but that's not really what we're seeing here. Hello there, Science Bob. That's our buddy Bob McGuire.
Some of the smaller pieces of black are interesting. That one right there, and that one right there. That one looks almost like a tornado.
Let's zoom in and see if we can see any shape to it.
Got a little narrow tail to it there on the bottom left.
Yeah, look at that. Interesting. Let's see if we can soften the noise in there for now. That's cool. That's neat. Let's do this processing. Yeah, you can see subtle overlying thin wisps here. Some here. Look at that subtle overlay of less dense material here. That's cool. So yeah, we're looking at many supernovae worth of material that have been laid down in the interstellar medium. Okay. Alright, so we'll go to 30 exposures here. We're at 29 now, one more. And then we can do a final save and move on. As the constellation of Cepheus gets up higher, we're also going to look at something called the Iris. And that'll be the first time we photograph the Iris with this new camera. So it's pretty exciting. Izabela wants to go to the Seahorse.
I see that. Soon, Izabela. Michael Hedrick has a question of you.
Okay, let me just save us out of here and get back. And save exactly as seen. There we go. All right. All right, this is the Gamma Cygni Nebula. It'll be up there in about 30 seconds. If you want to go to where they are, just go to SkyTourLive.org, behind my head, right there. All right. Let me take myself a little down. There we are. Okay, so... All right, Michael, now I can get to your question.
Mark, excuse me a moment, please.
Sure, go ahead.
Right back.
Yeah. Oh, Daryl actually accidentally hung up. I'll call him back. Let me just give him a call back and take care of that. Alright. Okay, there we go. Daryl's back.
Yeah, sorry about that. Share the screen, please.
Yeah, yeah.
I hit the wrong button.
I'm doing it.
I hit the red button.
The red button. Oh, never hit the red button.
I know.
The red button is always the bad button to hit.
Okay, there you are.
Okay.
Now, please excuse me. I'll be back in a moment.
All right, we'll be waiting for you. Okay. Now let's go back to here. And let's back out a little bit. And let's go look. We're getting close here. Let's make sure. There's Cepheus right there. Okay, so there's the Iris Nebula. Let's see if we can get to that, and when Daryl comes back, we'll also do the other one we've been talking about. So let's see if we can get to this. Sometimes far northern objects mess with our telescope. Let's hope not. All right. Okay, we're in this low light mode now. And we should be good here. All right, I think we're looking at this. So I'm gonna move us over there. The Iris is an interesting nebula, and the reason is because this is an area where there's so much dust that we don't see any hydrogen emission. We just see the illuminated dust, and it's actually so brightly illuminated in some places it actually looks the color it is, which is brown, and it's just lit up. I believe that this is it. I'm gonna do a test. I'm gonna do a quick shot, make sure we got it. I'll do, say, a 12-second test. And then I'll go back and change it as necessary. This will be the previous one coming up here. We're going to clear that. It is. Izabela says it's one of her favorites. It is really a beautiful... Yeah, that's it. Okay. Now what we're going to do is color correct and get rid of this here because we want to go into deep sky mode. Yeah, there's deep sky mode. Okay. This dark, you see there's no stars here? Well, there really are stars. They're just behind the dust cloud that's here. This is the first time we're taking a picture of this. I'm going to do this. I'm going to quit this, go back to 1 second, and go back to our low light mode for a minute. And the low light mode is going to be in place. See that real quick? We're going to see more. I'm going to drop us down. Hello, Daryl. Welcome back.
Thank you.
Okay, here's the Iris. And I'm just going to bring us down because there's some beautiful cloud here. There's also one over here. So I'm gonna move the Iris a little bit this way. Gonna move a little to the west. I don't want to go too far. I think we'll just do this for now. All right.
Did you answer Michael's question?
I think I did.
You talked about a quarter coin hundreds of miles away being the same apparent size of a star.
No, I didn't actually. Okay, sorry, I didn't see that, Michael. I'm sorry. Yeah, I've talked about a quarter coin. Okay, all right. That references to the nearest star to us besides the sun, which is Alpha Centauri, 4.3 light years away to Proxima Centauri, the small red dwarf. But the other two stars are kind of sort of like the sun. And those stars are very, much about the size of our sun in diameter. So the question was, how far would you move a quarter coin away from your eyes to make sure it's the same diameter as the real diameter in the sky of Alpha Centauri? And that answer is 725 miles. And there's no telescope on Earth that can see a quarter at 725 miles. If there was, we'd be imaging stellar diameters all day long. But we're not. And we can't. So I'm going to do a 25-second shot of this. I'm going to up our sensitivity to 250. So it's a little more noisy, okay? But we're going to see a little more detail. Okay. So here we go. We're going to get out here and go into deep sky mode. We're out of low light mode. And here we go, deep sky mode. And we're going to clear this. That's the previous shot. And it's up a little higher now. And as this sort of develops out, we're going to be able to see some really incredible and beautiful filamentary structure in this. Okay, so let's color correct. And then let's do an analysis here to do this. You can already see some of the brown coloring of the dust in this area. It's really spectacular. See that? That's going to resolve into even more beautiful brown dust. Yeah, look at that. So this is the Iris Nebula. You'll notice, as I said, that you don't see very much of that hydrogen ionization at all, so you don't see the red colors. But what you do see is this blue, and this blue is fascinating because it's really the area where the starlight is being scattered by the dust particles that are around this star. And this particular location has a fascinating location that's right here, and we're going to talk about that in a second. I'm just going to darken this up a little bit, go to the peak of our curve, just to kind of get us the best darkness for the view. Look at that, okay? And you'll notice this shape right here. It's like a keyhole, okay? You see that? You can see that through that hole, we're actually seeing the stars behind it, because this is dark dust that's obscuring the stars behind. That's why you don't see any stars in here except stars that might be kind of on the near side toward us, and stars that are beyond. Like, look how many stars. You should expect to see this many stars all the way across, and we don't, because this dust here is obscuring it. See that? Except there we're looking through it, and that's kind of cool. It really shows you the three-dimensionality of the universe really clearly. We only have 5 exposures right here, Daryl, so I'm going to just punch this up to kind of show what else is there. So you can see, here's that dark thing. I moved it over so we could see it. So that'll show up too. This will show up even better as we build more image. This is the first time we've seen the iris with this particular camera. So we expect to see like literally 1.5 to 2 times more detail in our imagery.
So for the hole we see to the right of the star, and we're actually seeing stars through that hole.
That's correct. That's what I was saying just now, is that you get that.
Well,
it's like a window.
My point is, per what Ray was saying earlier, I mean, I wouldn't call that a real void, for instance, but it's definitely a hole. It's not just, a cloud of dust.
Yeah. There's another one right here. Okay, and you see that it kind of extends out to here. You can see this dust cloud extent right here. Kind of sort of goes this way, and then down. There's streaks out here, all right, that'll resolve. This is a beautiful element that'll make itself clear soon. And in the enhancements, I've got those off. If I turn off the sharpening right now, it might show it even better right now. See that? That's pretty. Let's move this down. And let's actually move this out of the way. And let's go to full screen with this as we develop it. Wow, that's really cool. This little glow over here, this is amplifier glow. It's a glow from the camera, and we remove that in post-processing. It's not a bright star, just out of the field. With cameras of this nature, you just can't avoid this. Alright, let me bring up the histogram again, just temporarily. I'm going to color correct again. There we go. There you go. Look at that. So now you see this brown dust. This is really amazing. This is showing up beautifully. Really impressed with this. Laura Newbert's here. Hi, Laura. She says, what would be the estimated area of that dust? I'd have to get the distance to the Iris Nebula, which I can look up here. Let's see if it's here. We'll get a rough idea.
I already have it.
Yeah, I figured you probably read her question, right?
Yes.
Okay, well, let's see here. Now here, it says the distance is about
1,300 light years.
Okay, so this is right. Yeah.
And the nebula itself, radius was 3 light years.
Okay,
But
so
the dark dust is a lot bigger than that.
so this is the nebula here. We assume that's the extent they're talking about. That's cool. I'm going to take this down just a little into the weeds.
Red Angel, that's not correct.
What did he say? So tell
Said no dust in space.
Oh.
There is tons of dust in space.
Everything you're looking at here is dust. This is all dust.
Millions and billions and trillions of quadrillions and ooks and egads of dust in space.
Yep. I was had a Rascally Rabbits with us. Hey, Rascally. You're more than welcome, he says. This has been great. Thanks. So, Laura, to answer your question, it's probably this diameter that's about 3 light years. But now that we know how far away it is, I could precisely measure that and actually get all the extents of this and get that answer. I would just I have to go into Photoshop. I've got a setup in there where I can draw lines to do analysis and figure that out, knowing the size of our field and so forth. Oh, hey, let's do that while we're here. Let's annotate this. Let's see yeah, there we go. The NGC 7023, the Iris. There's the star Hipparchus 104291, magnitude 6.88 star. This nebula is a magnitude 7. That means it's fainter. The higher the number, the fainter they are.
Daisy and Zoe says, what is the makeup of the dust?
Excellent question. I can do it if you won't want to.
I would say mostly carbon. Other stuff.
Yeah. Carbon and silicon. It's very complicated. Interstellar dust is actually quite complex because in the depths of space, one of the things that happens is if there's not a whole lot of radiation to absorb in a dust particle, that dust particle's temperature, because you can have a temperature of an object in space, you can't have a temperature of space because there's nothing there to take a temperature of. Okay? And you need something. Objects in space either absorb radiation or reflect radiation. So the dust particles would absorb radiation from nearby stars, and so their temperatures, however, especially at distances out here, are going to be exceedingly cold. So most of the dust in this nebula right here is going to be particles of dust that, as Daryl said, might be carbon molecules, carbon-carbon. Carbon is really good at bonding with itself and other things. Carbon-carbon or silicon, the final stage end product of massive stars before they go supernova. And but those dust particles are not left alone. There's all kinds of other molecules and compounds that will form ices on top of them. We have ammonia ice, we have methane ice, we have formaldehyde, carbon monoxide, we have carbon dioxide ice, we have water ice, H2O. And those will form ice layers on these icy particles. and that ice can be melted by, say, a hot young star that might form inside this here. And when that happens, all that stuff is liberated and becomes part of the nebula, the slurry of life-making materials that will go into making a star from the gas in this area, like hydrogen gas, and planets from the dust that is conglomerated. So it's actually a very elaborate process that goes into making planets from this material.
Izabela called it soot. That's as good a word as any.
Yeah, the carbon. That's the carbon molecules, soot. Because in the outer atmospheres of these massive supergiants, okay, it's cooler out there. It's only about 3,500 or even 3,000 Kelvin. It's not degrees Kelvin. Those don't go together. Kelvin is its own scale. So 3,000 Kelvin, 3,500 Kelvin, that's actually cool enough to make a amazing set of molecules out there. So we'll get, as Izabela says, soot sometimes in these stars. And that can redden the atmosphere of a star as well. And some stars are this deep scarlet red. There's not a ton of them, but those are called carbon stars because the carbon molecules in that outer atmosphere of the star really deeply reddens the star. The color is just astonishingly beautiful. And we'll look at carbon stars at some point. Actually, we're kind of near one right now, but I want to finish this.
EMAD has kind of a loaded question.
Okay.
We understand there are many ways that there would be no life, dude. I'm asking, is there life out there? Yes or no?
Yes, actually, it's an agreed upon tenet that most of us in astronomy believe that yes, there's probably life out there. Is that life here, though? That's the question. I firmly believe that it can be and that it has been here and maybe still here, has visited us. Technology is beyond ours. I do believe that. And I'm not alone. Avi Loeb at Harvard believes that with me. He also knows. And I've worked with him a few times. He's a very nice guy, and he doesn't have a penchant for the wild and crazy. From a scientific perspective, it makes perfect sense that they would be here. And like me, I do a lecture around the country I've talked about many times where I talk about interdimensional space travel. Sounds like science fiction, but it's not. It's actually something that even Loeb talks about and says is a strong possibility, you know. So it seems to me that if they're here, they travel interdimensionally, because if they do that, they can get here in mere minutes rather than thousands of years. It seems far-fetched to us, but when you see the mechanism, the actual physics mechanism behind it, it becomes less far-fetched. And let's also consider that CERN overseas is actually just finishing up experiments with their ATLAS detector on the Large Hadron Collider, and the ATLAS detector has been working and capturing Kaluza-Klein gravitons, the KK particles that would be the crux, the centerpiece of this interdimensional travel. And Kaluza and Klein theorized their existence, actually a long, long time ago, I think in the 20s or 30s. And now CERN has been able to confirm them and show their existence. And that's pretty cool. And there's a whole story to that, but we won't get into that here because it'll make most of you fall asleep. See?
Laura, no, carbon does not create the auroras we see at sunset. Auroras are caused by protons, solar wind, and stuff from the sun hitting Earth's magnetosphere and ionizing gaseous elements, oxygen and nitrogen mostly in the upper atmosphere.
Yeah.
Way up in the upper atmosphere. If you're talking about the red color, no, that's not auroras. That's just sunset light.
Yeah, the red auroras are higher altitude oxygen auroras. The lower altitude oxygen auroras will appear green. Nitrogen auroras will appear blue. But the very, very high altitude oxygen auroras are going to be red. And it has to do with the transitions, atomic transitions, from those energetic particles striking the atoms in the rarefied upper atmosphere versus a thicker atmosphere.
Well, she said red sunset light, so
Oh, okay.
I mean that's what I was trying to address, not red auroras.
All right. Yeah, the red sunset light, Laura, is actually caused by, and I mentioned it earlier, the same reason we have blue sky is the same reason we have red sunsets, because the blue light from the sun is removed from the solar spectrum when you look through more air. And the molecules in the air scatter blue light very, very, very efficiently. So that's high frequency light, and high frequencies love the molecules in our atmosphere. And the molecules, the molecules love the blue light. So they will take in that blue light and send it off in every direction. So everywhere you look, our sky's blue during the day. But as the sun sets, we're seeing it over the curve of the Earth through more and more atmosphere. So more and more blue light is removed from the spectrum of the sun, okay, that's coming to us. So that's why the sunsets are always red along with the sunrises. And that's a fascinating physics principle, but it's Rayleigh scattering, it's called. But it's really neat. You can see this detail now, guys. Look at this. This is starting to look really detailed. And I'm going to just darken it up a little bit more. Wow.
Emed, my last question is, there intelligent life forms equivalent to our species neurons? Who knows? Somebody once said, looking out at the universe, it'd be a shame if there wasn't anybody around to appreciate it, wouldn't it?
And it would be a miracle if there wasn't. JCO77, what's up? Good to see you, man. Michael says, Marc, I love analogies. Can you give us any analogies to help us understand the sheer numbers of stars and galaxies out there in relation to grains of sand or world population or such things? Well, world population doesn't even come close to just our neck of the woods in the galaxy. Okay, with all the people on the Earth, like 8 billion people, well, our galaxy has like 150 to 400 billion stars. We think somewhere in between. So that would be one heck of a populated planet, Mike, in that case, right?
Arthur C. Clarke once said, I believe this was in the novelization of 2001: A Space Odyssey, and this was the numbers as they knew them back in the 60s when he wrote it. He figured, looking back over the history of humanity on planet Earth and doing some number crunching, that there have been about 100 billion people on planet Earth over the course of history, prehistory, over the course of humans on Earth. And it was thought at the time there was about 100 billion stars in the Milky Way galaxy, and he said, for every soul that ever lived, there burns a star.
That's a very pretty analogy.
Yep.
And the truth is, if there's life out there, I told you this before, I firmly believe they are here. And I was on a nuclear submarine as a guest some decades ago, and a very fast-moving object was seen on the sonar. It moved several hundred knots underwater. And because I do work for the Navy with my other business, which is a model making company, I actually had a chance to work for the Joint Chiefs and the Office of the President, and I talked to the Joint Chiefs and I asked them about the program called the Fast Mover Program. And even though I had the clearance to hear it and talk about it, if you're not read into the program, they're not going to tell you about it. And so I was told very politely by one of the chiefs, okay, that he couldn't talk about that program. Now, in our chat is someone else who was on a sub and saw something similar. And if he wants to speak up, he can say something. But he was also on a sub and had a very fast-moving object go through their sonar as well. So I leave that to you, and you know who you are. If you want to say something, you may say it. And he's in the chat.
Supercavitating Soviet torpedoes.
Yeah, those are the squall. The squall goes 200 knots underwater, but it's the loudest thing in the ocean, you know. And if you're going to listen to the squall, there's no mistaking it, and it's a desperation weapon. You fire it, and it goes in pretty much a straight line. It's a rocket-powered torpedo that makes a rarefied steam extrusion off the nose cone that actually allows the torpedo to go through its steam. It's this vacuum of steam, almost this vacuum cloud, and that makes it go faster. But that's the fastest thing. It doesn't last very long, and again, it's a rocket, but it's really loud. This thing was almost silent, which makes sense based on the physics that I talk about how they actually can maneuver. But if he wants to talk about it, I'll let him make that decision, because I'm not going to out him unless he wants to talk about it.
Actually seeing a little red there at the top of the
I
iris.
see that, yeah. And I'm just... There's the dust. You can see that dust very well. I kind of zoomed in so you guys can see this. Okay. As you can see, it was Science Bob. Okay. And he said, I heard a fast object when I was on the USS Hampton in 1998. The story is almost identical to Marc's. We are brothers in USO Weird. Yeah, we are. USO Unknown Submerged Object. I gave him a chance to... I didn't want to say it unless he wanted to come out and talk about it. Because you know what? I don't care about stigmas or whatever. I just don't. I think that we want to get to the truth. So thank you, Bob, for coming out and telling folks as well. Look at that. This is just beautiful. I'm going to, now that we have 50 images stacked. Yeah, thank you, Bob. I'm going to pop this up here just so we get a little more contrast. Remember I talked about the brown? See the brown? That's... that brown dust, carbon is typically very black. This brown dust is probably a mix of carbon with silicon atoms and other compounds. And you're probably going to have some hydrocarbons in the ices on these dust particles. So literally, you're literally looking at the slurry of material that makes planets and life in time. And you know, one of the songs that we've written for SkyTour talks about life beginning in the dark. That's precisely what happens. Let's move this over now and get the telescope back into view.
As Carl Sagan once said, we are made of star stuff.
That's right. That was always one of my favorite lines. Look at that. That's pretty. I'm gonna name this and then save it. Okay, this is the Iris Nebula.
So we are in Cepheus now.
Yeah. Yes, I know. Complain all you want.
What? I'm not complaining.
No. The screen. The program was complaining because I renamed it.
Oh, I see.
Yeah, so we're good. Yeah, no, it's gonna be fine. Okay. So here's our full image of the iris right here. This is what's up there. And when we process this, we're going to be able to pull out a lot more data. There's another beautiful dark cloud right here that we'll pull out. As you can guess, I'm somewhat familiar with the area. All right, let's pull this back just before the peak. And let's pull this in just to push really hard to see what else is there. Okay, and then I'll actually bring that peak down.
And Fantasy has a question for you.
Yeah, see, some of these denser areas are darker. Okay, what's Fantasy saying? Let's see. Hey, Lubo from China's with us. How much longer do you plan on going, Mark? Oh, just so I know. For my own SkyTour adventure tonight. Looking at the time, it's about 1 a.m. Probably another half hour, minimally. Time in Arizona is 9:54 Lubo p.m. He's asking about the helix. Wow, look at that, guys. See that dust? That's really fascinating stuff to me. Dark Nebula is my hot button. Okay, we're going to go to 60 here, and then we're going to go to another Dark Nebula that we have never imaged before.
Never?
Did you see it in the database?
The Seahorse?
Oh, we're going in Cepheus? That's the one you were talking about?
Yes.
Oh, we have. Sorry.
We've done the Seahorse.
I thought this was in Sagittarius. I'm sorry. Yeah. Science Bob says, also want to thank Mark for all his advice when I was getting my astrophotography rig together. He saved me weeks of searching and frustration. Oh, hey, that's okay, Bob. You're more than welcome. Thanks, Izabela, for filling me in on that as well. She says, we did. It was one of the most challenging images for processing for me. Yes, it was for you. Yes, I know. And for me, too.
You just haven't done it with this camera yet.
No, and this camera is actually it's tuned and it's more sensitive. It's a smaller field of view. It's more sensitive than the previous camera. And we have more pixels to show more detail. So actually, this is a good balance. We're going to try that. All right, just a second, guys. I'm going to do one more correction here. Yeah, there we go. Now that this brown dust is very, very clear. All right, 63 shots, and then we'll save it. Now, real quick, I've told you this before. We take one shot, we take a second shot, align it with the first, stack it on top, and we make an image sandwich. This is an image sandwich consisting of 63 images all stacked together. The dim dust, like see this now, look at that one. That one was invisible before, now it's visible. Okay, the dim dust is made visible because it's actual data, but the noise that is caused by these digital cameras is averaged out when you actually stack more and more and more of them with the noise going all different places. It actually gets averaged out, so that's really cool. Okay. I'll save it again because I got one more. Alright. And this will save exactly as seen. Alright, that's the iris. And now we're out of here.
I'm out of here, dude.
We're going to go to the Seahorse. I think we can see the Seahorse now. Alright. Alright, let's go. What's the number on the Seahorse?
You had it earlier. Give me just a second. I'll get it.
Yeah, I know. You're right. I did.
LDN 1082, the Seahorse Nebula.
Oh, that's right. Okay. All right,
1082.
1 second. I'm going to actually... I'm on that right there. I'm going to just do one more thing. I'm going to bring this telescope a little north, center on the star that's here, and synchronize coordinate systems so that we will be exceedingly close.
Izabela asked the question, what is there between the nebulae? Are there other nebulae that are too small to see?
Why not?
Well, in between visible nebulae, it's either empty space, stars, or dark nebulosity, the dust clouds.
Yeah.
And if they're too small to see, they're too far away. It's not NGC, it's LDN.
Oh, duh. No wonder. Yeah, I knew that too. You told me that. Yeah, Lynn's Dark Nebula Catalog 1082. And that's going to be up here. Okay, let's see where that is relative to... Well, that's pretty high in the sky. A little closer to the pole, but I think that'll work. This red square is our field of view that is represented here. Okay, let's dump out our... Alright. So now we're gonna go and move the telescope to that location now. So it's going to point a little bit more. There we go. You'll see the STLS crosshair show up in here. Here it comes. There we are. And you'll notice when we pull in here, you see these stars here? There's 3 stars. This is upside down, remember now. So on the right side, we should see those 3 stars, and there they are. So we actually have a really good... we're in a really good location right now. We've got this. It's in here now. Okay, I can even see some of it. All right, we're gonna do this. Gonna be a 25-second shot. And I'll stay at 250 sensitivity because I noticed that the iris was a little grainy for a while. So it's an interplay between this graininess and the smoothness. So again, we're just trying to show some really cool images to you. All right, 25 seconds and we're off and running. All right, let's get the live stack. You'll see the iris in our image buffer. This is the last shot we took. Look at that, all that beautiful nebula. Now we're going to see something similar now. I just saved it again. I'm good at this. All right. All right. Well, I guess I'll clear it. Okay, there we go. You can see a dark nebula piece right there already. I'm going to zoom out. Obviously, we're only getting a part of it because of the fact that this field of view is smaller than our previous field of view, but it's more sensitive. Look at that. Look at that tendril. It's already starting to show very nicely.
Yeah.
Wow.
And forking up toward the top left too.
Yeah. Up there and down.
Ray, I remember Carl Sagan on the Tonight Show before he got really famous, like before Cosmos. He used to appear with Johnny Carson on the Tonight Show.
He did.
Back in the 60s.
Saw him as a child.
Me too.
Oh, this is beautiful. Now, folks, if you're interested, you know, if you like what you see, you know, you could actually become part of the SkyTour family by joining our Patreon. We absolutely would love to have you with us. You know, so you could, you know, if you joined our Patreon, then you'd be able to capture with it. You'd be able to see some of these images in very, very fine detail because we do final processing and make them available to our Patreon members. And on top of that, if you actually like the images you see, one of the things you can do also is in the upper right hand corner here, it's up there, you see it right here. You can go to our Etsy store, SkyTour Shop, and SkyTour Shop, and I guess I should probably kind of move that where everybody can see it. All right, SkyTour Shop is our Etsy store, and the Etsy store is showcases our work. We actually have these beautiful images you see here of stuff we do final processing on. We put them on blankets, we put them on sneakers, we put them on mouse pads, mugs, cups, water bottles. I mean, and we send them out everywhere. So it's really cool if you want to get something like that. I would very much enjoy that. And we're always adding to our list. Always adding to the list.
That's showing up very nicely.
It is, isn't it? I'm going to go back a little bit. Look at that. That's a beautiful...
very red stars in the field, too.
Yeah, that's true.
One over on the far left, one on the mid-right.
Yeah. And then some very small ones. Those are probably red giants of some kind. That's really pretty. Yeah.
People supposedly see a seahorse in this.
Well, we're not seeing the whole thing, though, unfortunately.
Well, I know.
Yeah.
I know the view showing your camera field in Stellarium.
Yeah.
Looked like it showed kind of an oval shape.
Let's go back.
Filling the field. You see that?
Yeah. That's...
See the oval shape?
Yeah, this.
Yes. Maybe that's just one of those things that Stellarium does where they highlight an area sort of like around Gamma Cygni, you know, the biggest square nebula you see.
Yeah, right.
Shape.
Yeah. I think that's just they actually trying to mix a actual photo that someone took with the background stars. That Stellarium doesn't have all the stars. Izabela, thank you for putting up the Patreon page and the Etsy store page. Thank you so much. Izabela says, I see my torture today. Guess what? It's going to be easier. It's going to be easier, Izabela, because this camera has more sensitivity and you can see details already, and we only got 12 shots. This is really nice because at this end we're capturing the little piece down here. This might be one of those mosaic things over time that we should do.
Would you go down or up or sideways or?
I'd probably go up here, and to the left, out to the left and higher, and then maybe down, so you can actually get this diagonal set. Izabela, I love that. I see my torture today.
She was talking about that earlier.
Yeah.
I guess she had a hard time processing
Yep.
the Seahorse when she did it before.
Yeah, but she's so much more seasoned now.
Yeah, it's a better image too.
Yeah, a lot more detail. I'm gonna color correct. The curves will wander over time, and so if you color correct, you actually see like that. We correct it, and now you see it looks better. These dark knots in here. This is where life begins, guys. In these dark areas, this is where the fundamental creation of planets and stars within there, if there's enough hydrogen gas, and there certainly would be, will occur. Alright, JSCO has a question. JSCO 77 says, do you believe there are creatures living in space itself? Example, some things seen on videos from the space shuttles and blah 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 appear to be alive. Actually, I have to say no, and qualify that. I do know that there are creatures that go into a state called cryptobiosis, the tardigrade, for instance. And there were tardigrades on the outside of the ISS, and they were still alive, but they were in cryptobiosis. So when there's not enough water, not enough of a proper environment to survive in, they go into that suspended animation, essentially. So I think that's pretty cool. So
I think.
Go ahead.
Well, it's a Star Trek kind of thing, but
It is.
It's life as we know it. Like in Star Trek, there are the superior beings, ethereal, floating around like balls of light and stuff like that.
Yep.
And I'd heard speculation once about, like the Horta on Star Trek, that
no kill eye.
that it could be, the biology and the metabolism is so different that like 100 years would be like a day to one, something like that, or 1,000 years. It's like trees.
Yeah, actually, and it's very interesting you say that, because there has been some studies done just very recently showing that even animals here on Earth register time differently. For instance, if a bird registered time the way we do, it could never fly at high speed through branches of small bushes and make it through alive. It has to experience time at a different rate, so that it has the reaction time to get through tiny branches as it moves 15 miles an hour through a crowded branched tree and not hit a single branch. We couldn't do that, right? So
this is true, but
so it senses time differently, Daryl. That's one of the things about it that's interesting.
well, and I think you could tie that to lifespans, measured in number of heartbeats in a lifetime.
I guess that's true too.
That little fast-moving critters, fast-reacting critters,
Yeah.
like birds. They typically have shorter lifespans, but their hearts beat much, much faster.
That's right.
Imagine how many times a second a hummingbird beats its wings.
Yep.
I couldn't do that. You couldn't do that either.
No. Okay, the annotation doesn't see this yet. So as far as creatures living in deep space, I don't believe that's true. But just because I don't believe it's true doesn't mean it's not. The worst Star Trek The Next Generation show, the very first episode, was the worst one, and that was Encounter at Farpoint.
Yeah.
And, where they see this beautiful city, and it's got all these chambers, and then people realized, the folks on the Enterprise realized that that's because it was a buried creature that was being held captive. And when they figured out a way to release it from captivity, it went out into space, where it became this gigantic creature, like a jellyfish, a space jellyfish. That's fanciful, but
weren't there two of them? They
yes.
kind of joined at the end of the show.
Yeah, and that was why the Enterprise was brought there, because one of them was attacking the settlers, and it was attacking the settlers because of the fact that it was keeping its mate hostage. You do the same thing if your space jellyfish mate was being held hostage by these nasty humanoid creatures. Very funny.
Ray said, some believe that there were very advanced beings in the universe. All have been annihilated or annihilated themselves. That has a name. It's on the tip of my tongue, and I can't think of it.
Oh yeah, I know what you're talking about.
Kurtz's talked about it.
Yeah, it'll. The thing about that, and we're still waiting for this image to come in even better. We got 28 images shot so far. You can see the stack is looking beautiful. We're seeing this gorgeous tendril. Izabela, I'm trying my hard to make your job easier. And my own, to be fair. And there's more out here, notice. It's faint. We didn't see that before in here. So, as far as life in the universe, one thing I would say is, I think if there's going to be life, it's going to be carbon-based. And I've talked about this quite a lot. I lecture about this quite a lot. Carbon is the granddaddy of all elements in the periodic table. It has these 4 electrons on the outside, 4 valence electrons that can bond with many things. And it's like it's nature's best tinker toy. Okay, it allows for bonding and breaking of bonds, even more especially, much more easily than any other element on the periodic table. It's the most flexible element. And it's also the 4th most abundant in the universe. So being 4th most abundant is very important, because it means it's very plentiful, of course, and it means that life will have a chance, a lot of chances, many chances, to form based on carbon. So I think it's going to be the dominant life, sustaining and life-giving element in the entire universe. Now, 3rd most abundant is oxygen. So you can see the tie between carbon and oxygen is from the very beginning. So carbon in the periodic table sits above, column-wise, vertical column-wise, silicon. So when Daryl was talking about the Horta in Star Trek, Devil in the Dark episode, actually, that was a silicon-based creature. The problem with that is that silicon tends to make crystalline structures, and it makes very tenacious bonds that don't like to give up their atoms once they make a molecule. So life requires flexibility in the bonding process. C6H12O6, okay, the sugar molecules in your body are broken down, and they're made and broken by your body all day long, all night long. Silicon bonds would not be broken very easily. It requires a lot of energy to break a silicon bond. So a creature based on silicon would have to really be much more simple. It couldn't support a variety of processes the way a carbon atom could. So, and I use this analogy, I talk about sand on the beach. That's silicon dioxide, a silicon atom with 2 oxygen atoms. Okay, so, and I always say this too, you tell all your friends when you walk on the beach with them next time, you're walking on mostly gas. 2 oxygen atoms versus 1 silicon. Now the rub is the silicon atom's a little bit bigger than the oxygen atom. Okay, however, you're still true that by atom count you're walking on literally 2/3 gas and 1/3 of something solid, so to speak, and that's kind of funny. But those bonds are hard to break. So beach sand doesn't break down very easily, does it? It doesn't break up when exposed to the sun. Okay, your skin exposed to the sun, carbon bonds are changing all the time when you're exposed to the sun, and even regular room lighting. So that process is something in the universe that is sort of a template, isn't it? That carbon is a kind of a template for life in the universe. That's very important, and something that means that carbon is probably the predominant method for the formation of life, which also means alien life elsewhere probably is carbon-based, and thus to be carbon-based means you require oxygen, because carbon-based life forms utilize oxygen to help it metabolize, live, survive, create processes to for continuance. So an alien species is going to look for oxygen in your atmosphere. If it's looking for a planet like their own and they want to move and they're capable of it, they're going to look for oxygen in the atmosphere. So this kind of thing is something to understand. We stand out like a sore thumb because of oxygen. Now I know that Stephen Hawking said we should hang tight and hide from interstellar technology and alien life out there, right? And you've heard that too, Daryl, I'm sure. But the creatures that are looking for oxygen in an atmosphere will have long since found us. And the reason is because we started building up oxygen over 2 billion years ago in our atmosphere, long before there was any life on the planet of any consequence. These little blue-green algae, these little tiny phytoplankton, cyanobacteria, started life and started making oxygen in our atmosphere. And for them, oxygen's a waste product that they're giving off. It's not like something they need for life. They give it off as waste. In fact, too much of it is harmful to them. So they would make oxygen, and so it became visible billions of years ago to life in the galaxy. And time is something the universe has in abundance. So it's very possible we've been well noticed. And remember, we're as Carl Sagan also said, we're the pale blue dot, right? And as the pale blue dot, we've been, I think, under the watchful gaze of alien life for a long, long time, because we're very, very noticeable if you're looking for it. We're doing it now with our primitive technology. So,
The idea I was looking for is called a great filter.
Oh, that's correct. Yeah, you're right.
That there is some step along the way from simple life to Kardashev scale life in the intelligent life in the universe.
Yeah.
That there is something blocking it somewhere along the way, filtering it out. Why we're not seeing anybody.
Yeah, that's a possibility, and I know that question came in earlier, and thank you for bringing that back up, because it ties in with Izabela's. She writes, Mark, what is your personal theory for why the aliens don't contact us? They don't really hide, but don't say hi either. Okay, well, that's also true, but let me just offer this up. I can't tell you why they haven't contacted us. Now, wrongly attributed to Enrico Fermi was the principle that he was claimed to have said, oh, well, where are they, right? The Fermi paradox thing. Well, he was actually talking to a lot of nuclear scientists that were working together, and they they all asked this question of each other, and it was sort of attributed to Fermi, but never mind that. Anyway, the fact is, in my view, if they're not contacting us, there could be reasons. Among the reasons are the same reasons that we don't contact herds of elk, because we know that they could turn on us and kill us, because we are like 1,000 times, 100,000 times smarter than an elk. But we know that elks can kill us if they kick us with their feet. So it could be that. It could be that they're here but hiding, and for them, hiding from us is not going to be very hard. Their technology is all that stands between us and them, and we are piercing that veil little by little. Okay, but it could be the elk principle in the Yukon, hunting elk. Okay, you're going to hide behind a blind to look at elk, otherwise they're going to run away or they're going to attack you. So it could be that they're hiding from us.
I don't know if elk is the best choice. You go to Estes Park, Colorado, you can't get away from the darn elk. They're out in people's front yards all the time.
Yeah, I guess that's true.
And during breeding season, they go out and they fight each other, and they go and use their antlers on cars and people and all sorts of stuff.
Yeah. But you get the point. You get the point. It can kill you. If you get in the way, they'll kill you. So an alien life form might skirt around and avoid us, okay? And if it avoids us, that's probably smart on their behalf. And because they can avoid us easily with their technology, I think that they're in the deep oceans. I think they can hide in the deep oceans because based on the propulsion methodology that I lecture about, they could very easily be in the oceans without any problem, and that's something that we would have to consider. Now, Fantasy says they got cloaking technology like the Romulans. Well, effectively they could, and the way that would work is if they travel interdimensionally, then they wouldn't be visible to us unless they wanted to be, all right, or unless the consequence of their activity and their propulsion methodology makes them so, and that's a possibility as well. Hi to Pesty Pig, how you doing? Make sure you subscribe to us, guys, if you haven't subscribed, because look here we are. The Seahorse is looking beautiful, and we have 52 images stacked. I'm going to save it now. So the bottom line is that's one reason they may avoid us, because they know we can hurt them. The other reason could just be a consequence of their mobility, the way they move. Again, if they're interdimensional, then while they're moving, they would be translating into our 4 dimensions and into this 5th dimension that is predicted by the Kaluza-Klein hypothesis. And if they're doing that, then they wouldn't be visible to us. They would literally vanish right out of your sight. It would literally disappear right in front of you. You'd reach for them and they're not there. And you might say, this is not real. This can't be real. This has to be a dream. But in fact, it is real, because it has to do with transitioning out of our 4-dimensional world. So everything we've done is in the 4 dimensions. Going to Pluto, leaving the solar system, going to Mars, going to Venus, okay? Russian Veneras landing on Venus, all done within our 4 dimensions travel methodology, and it took lots of time. So if it takes that much time to travel within our 4 dimensions, we obviously want to find a way around that, don't we? We want to find a shortcut. Now, in 1994, Miguel Alcubierre came up with that Alcubierre drive, which was a warp drive, they called it. And they would basically fold space, then cross a little tiny gap and unfold space. That folding required a warp bubble. The warp bubble required massive amounts of energy, and you had to do it over and over and over to get to a destination. Theoretically, we could get to Alpha Centauri in 5 to 10 days. That's a lot better, as I've said many times, than the 10 to 12,000 years it would take us with our current technology. However, if we go using this dimensional shift, some physicists have calculated it would take us 20 minutes to get there. A lot better for crossing a galaxy. Wouldn't you say, Daryl? Yeah, whatever. Okay, you know what? You know...
That's highly speculative.
Yeah, but it's true. It's true that it's highly speculative.
It's maybe possible,
Yeah.
but it's highly speculative.
Well, you said yourself it took 66 years to go from Kitty Hawk to the moon.
Yeah.
Okay. If you think about lowly humans getting to the moon in just 66 years, 66 years isn't even a tick mark in the life of the universe.
Yeah. 6 years isn't a tick mark in the life of a good tree. Or
Right.
a horta, for that matter. This is getting silly.
This is not silly.
I think, we've been around as a species, 50,000 years, 100,000 years, and we've been technological for just a few hundred,
Yep.
really, in modern sense, 100, 150.
Yeah.
You take life that has managed to survive and has been around for 1 billion years or more, those people, if they even still are in a bodily form, those beings, I dare say they have very little interest in us. They're so far beyond us, we're like ants beneath their feet.
Yeah, that could be, though, subspecies in the universe. Yes. I agree with that. However, maybe there are other species that are more advanced than us, however, not advanced to the point where we're strictly just ants. We might be other carbon-based life forms that might be of interest because they may be scientists, they may be explorers. Because that's another factor about life on Earth. And if we use life on Earth as any measure, when you look at life on Earth, all right, again, created in dark clouds like this, then what you have to understand, and you do, I'm just saying that as a rhetorical thing, what you have to see is that life like us, and life like every creature on this planet, that's made of all DNA, by the way, that's another commonality of every life form, every single life form has imbued within it one particular overriding characteristic, besides DNA. They actually express curiosity. Every life form has curiosity. All right, in whether it's rudimentary or or refined, like with us, okay, or dogs and cats, okay. Curiosity is part of life's path for most creatures. Maybe not, even maybe on single cell levels. I'm not sure, but on multicellular levels, curiosity is imbued in those creatures. So if it's happening here, that all the life forms on Earth have curiosity all throughout time, isn't it possible that that too is a template in the universe? And so life forms created elsewhere are going to be curious, and they're going to want to look up and figure out what's going on. And why? Because they're trying to establish some type of mathematical equation about the universe? Only possibly, but most likely they're going to have a curiosity to know what's out there. And so that's what drives explorers. That's what has driven every explorer on this planet. Curiosity and the overriding decision to expand their territory and see what else is out there. And
Curiosity killed the cat.
it sure did. There's a lot of cats that are alive.
I dare say most critters, their main concerns are, is this going to hurt or eat me, or can I eat it without dying? Is this going to fall on me? And, stuff like that. That's about it.
That's also decisions life makes, yes.
Let's go to Douglas Adams and, the dolphins. The dolphins decided to leave, and so long and thanks for all the fish.
Yeah, right. Yeah. That's true. And dolphins are a good example of life forms on the planet that are highly evolved. Why didn't they ever get intelligence? And the reason is because in their niche, in the water, where they stayed, they never had to evolve past where they are. But just because we know about evolution doesn't mean it stopped. They're still evolving to other forms potentially, and maybe refining their brains and actually learning more as they go, as generation to generation. So maybe evolution is helping shape them as well. Okay. However, in their particular niche in the ocean, like the octopus, they have reached the pinnacle of that particular niche. They're the kings. The octopus is the king of that niche, and I think it's probably one of the most intelligent creatures in the ocean. And you say, well, it can't do mathematical equations. Of course not. All right, but then again, it was never under the environmental pressure to develop that capability. So
there was a series of books published back in the 70s called the Coevolution Quarterly. They were put out by the people who published the Whole Earth catalog back in hippy dippy days.
Yeah.
And Coevolution Quarterly was a very interesting book. I subscribed to it. I probably still have copies of it around here somewhere. And each issue kind of focused on a certain subject. And
yeah,
one of them was, what is a human being? And at one point in that book, they said, are dolphins human?
Okay.
And the answer they came up with was yes. They're not literally human, but they're sufficiently evolved that, are they really roughly as smart or smarter than we are, but in different ways, non-human ways? But still, are they evolved enough to call them human?
Yeah. Hello there, Firehorse Creative. Nice to see you. Thanks for joining us. Yeah, each exposure is a live exposure, but stacked, you're right. So we're seeing it moment to moment, and every now and then you might see a satellite trail come across, because that is what was caught in that live exposure. Live exposure is right here. Is 25 seconds that you can see over there on the right. And as I said, this is probably the most important field in the entire screen. It tells you how long we're exposing it for. This one's the next one, most important, the gain, the sensitivity. We're at 250 right now. We can go to 450 with this camera, but then we get lots of noise in our image. Okay.
Whoops. Excuse me just a moment.
Sure. All right, so we're going to close up here with 75 on this particular object, and we're going to move to another object. All right. And Izabela, I think you can see that you're going to have an easier time processing this, as I will. This camera is so much more superior to our previous one. This is the ASI 183 MC Pro. We were using the ASI 294 MC Pro before, but it wasn't tuned to this focal length very well. And so we were out of the optimal range for that camera, but we're not with this. Okay. Fantasy. The only thing the Dolphins can do that is human is play football in Miami. I was waiting for someone to make that joke.
What joke?
I just said it. Oh, maybe you weren't there.
I wasn't here.
Yeah, the only thing Dolphins can do is that is human is play football in Miami. That was fantasy.
Oh.
That was good. All right, Fantasy was looking at M22, which is a globular cluster just above the teapot in Sagittarius. That's cool. Yeah, Izabela, it's good enough as it is. I agree with you. I'll save it one more time, and then we're going to move on. All right, here we go.
I bet processing would really do wonders on that.
Well, it's gonna make it beautiful, because you can see all the details and nuance now.
Yeah.
Yeah, we couldn't before. It looked mostly dark.
Speaking of fantasy, that reminds me, he asked earlier how late we might go. Fantasy is a general thing. I turn into a pumpkin around midnight Mountain Time. So 11 California time or
2 o'clock my time.
2 o'clock Eastern time.
Yeah.
And we usually wrap midnight, a little after.
Yeah, so now see, there's been times when Daryl's turned into a pumpkin and I just kept going. JSCO77 says, please, one more. Oh, all right. I guess we'll do this. There's another one, though. I want to see. Where is that?
I'm a ways away from turning into a pumpkin so far.
Yeah, all right. Where's the cave? What's the NGC number for the cave?
Just a second.
I might be able to find it this way. Okay, I found it. Let's see how far away we are from that. Okay, it's not too bad. Let's just do, because the cave has these beautiful pillars. All right, we'll check out the cave. Let's see if we can get to the cave without blowing up our telescope.
Sharpless 2-155.
That's exactly right. Okay. Here we go. So we should see the cave as a nebula that will be in our view here. Looks like there's something here. I think that's the north part of it. Let me just do a 20-second shot to see if this is where we are, where it belongs. I think it's right there. Let me just clear that. And clear that. Okay. And we'll get rid of that. Let's see what we got. Oh, how about that? We were actually just slightly... We're out of round with our star images for that. Let's see what the next one will be. Here we go. Oh, there it is. Yeah, we were right. There it is. Oh, that's a beautiful placement, too. Okay. We can let this keep going. This is the Cave Nebula. It's actually a very cool nebula. All right. JSCO says, we saw one of Flash's ships here live one night. Marc went silent, moved on, and I believe I'm the first to mention it since. Flash Gordon? Alright, let me just raise this a tiny bit. The LiveStream is politics free, guys. It's a very divisive topic these days. Okay.
It's very grainy.
Well, I know. Look at how many. We have 3 exposures we've taken.
Oh.
All right. Here's what I want to point out to you guys. One other thing too. In all these objects, when we see these objects, there's always cool things that you just don't know unless you get them pointed out. The other night, we actually saw Cygnus X1, which was a star that had a black hole associated with it. And tonight, we're looking at this right here. See those 2 little stars right there? I'm sorry, that's not it. This is it, I think. My mistake on that. Yeah, not this guy. It's this guy right here. Inside this little cloud, this is called a Herbig-Haro object. And they are stars that are in the process of winking on. You know, the fusion process, they're protostars that are in the process of actually turning on. And that's actually pretty cool. We see Reflection Nebula here. Again, there's all dark clouds of dust in here. You see that? Okay. And this is called the Cave because of this interesting little feature here. All right, let me...
Would it be advantageous to bump the camera toward the top a little bit?
Actually, it's already there, see?
Oh,
I was looking at a
okay.
lower... I was scrolling down.
I see.
Yeah, see, all of our exposures are coming in well now. This is good.
Science Bob, the other night we talked about movies and stuff like that a lot too.
Oh, we did.
Yeah. Some of that was just fun talk while the camera was doing its job.
Yeah, well, we can still talk about that. Yeah, this is cool.
Oh, you want to talk about a movie?
Sure, why not?
You're talking about the super fast object underwater. Reminded me of a... You ever see a movie called The Bedford Incident?
Oh, I know about that. Yeah, I heard about that.
Yeah, it's a black and white, early 60s
Yeah.
Cold War movie. Richard Widmark plays the hard-as-nails captain of a U.S. destroyer playing cat and mouse with a Russian submarine. And your talk made me think of that. Sidney Poitier is in the movie. And Wally Cox is in it.
Underdog.
And, yeah, he's the sonar guy, remember right? And there is, I can't think of the gentleman's name, but he played Dano on Hawaii Five-0.
Oh, yeah.
The original.
Young kid probably in that movie.
Yes, he was. The captain was really riding his butt hard in the movie. And turns out he doesn't handle pressure very well.
Yeah.
I'll just leave it at that. Heck of a movie, though. If you ever want to see a good black and white not World War II, but a Cold War movie.
Yeah.
Richard Widmark is great in it, too. He's just hard-bitten.
Richard Widmark was always good at playing the hard, captain and so forth. He was actually good for those roles. Because he had more than that. Are you talking about Danny Williams?
Yes.
Yeah. That was Dano. Book 'em, Dano. Okay, Steve. Yep.
Yeah, Widmark leans on Dano a little bit too hard and manages to start World War III. I'll just leave it at that.
Well, that's kind of like everything. All right, let's reduce the noise a little bit and see where we're going. Wow, that's pretty cool. So in this one, we have a stellar nursery. You can see here, there's a little blue. So in this dark nebula that's in here, it is scattering some of the starlight from nearby, probably from in here, these bright stars, if they're out there at the same distance. And so that light's being scattered, and so we see a little bit of the blue. Where we don't see scattering, we see it as this blackish brown stuff like we saw with the Iris. Okay, so blue reflection nebula is dust, like right here. That's blue reflection nebula. That's dust, the same as this here. It just happens that this particular nebula exists because the the dust in this region is probably affected by that star right there. And that star is probably scattering the blue light. Maybe this star is helping it too.
Sam Meth says Dano's name is James MacArthur.
I thought it was Danny Williams.
James MacArthur. I think he's right. That rings a bell.
Okay. Maybe Daniel Williams was the name of the character.
Maybe. When Hawaii 5-0 hits Dano.
Yeah. Greyhounds was a good movie with Tom Hanks. That's right. Okay, our filter for full width half maximum is proving useful. It's actually keeping our stars smaller. So we've had 4 failures. All the rest are good.
There's only one Tom Hanks movie I like.
Oh, you're talking about Castaway.
No.
Okay.
Joe versus the Volcano.
Oh, that was a good one too.
Yeah.
Yeah,
I love that movie.
That was a funny movie.
Yeah. Him and Meg Ryan and Abe Vigoda, Fish from
Oh yeah, Barney Miller.
Barney Miller. He is also in the first Godfather movie.
Yeah.
With Robert Stack, I think, was in it.
Yeah.
I haven't seen that, Izabela. I've seen clips of it.
Oh, A Quiet Place. Don't watch it with your back to the door. A Quiet Place is about an alien race that comes to the world, and they're extremely sensitive in hearing, and so the population of the world now has to go to quiet mode, because if you make the slightest noise, like silverware in a drawer, these creatures will come in and kill you and find you. So the whole movie's about being quiet and making noise to make diversions. If you see the first one, it's very, very disturbing, because there's a little kid that starts screaming, and, well, you can guess what happens. Oh, Major Matt Mason would have been a great movie, Donald Kunzer. You know, I have an original Major Matt Mason action figure. I have the the moon crawler. I have several. So it's actually pretty valuable now.
I've never seen A Quiet Place. I've never seen The Last of Us either, but they kind of remind me of each other, just in the clips I've seen.
Well, A Quiet Place, like I just told you, is what it's about, kind of. It's about an alien race coming here. And basically just vivisecting humans if you make a slightest noise. And you see that in the trailer, so you know that's what's coming.
Yeah.
Last of Us, I don't... was that from I never saw. Is that a virus that killed people?
Cordyceps. And I think the people who made the movie The Last of Us saw the very same piece of film that I did. It was on one of those David Attenborough nature shows on BBC. It showed a fungus called cordyceps that infects insects.
Oh, yes. Turns them into zombies.
Yeah, and it grows out of them, and The Last of Us is like if cordyceps attacked humanity.
Wow. Well, it's a cool premise.
It's pretty gross with those
Oh yeah,
shots I've seen of it.
I would guess it is. All right, let's punch this up massively to see what else is there. It'll be a real powerful punch. Look at that, all this dark nebula. See it all? That's what's in here. Okay. And we have streaks of nebula too, like this. Look at that. These streaks of nebula make it look like there's lines of stars because they're hiding some of the stars. Alright, let's pop that back down. Bring it back to reality. And let's kick this up a little bit. Okay, there we go. And right now we're at our peak for the black level, so we don't want to go any further than that because we'll start losing data. But that's pretty neat. That's the Cave Nebula, guys. And I really like the movie Arrival. That was really good. Sunshine?
YouTube offered me the theme music from the movie Sunshine a day or two ago, and I heard the music years ago and really fell in love with it. It's a classical piece, Adagio in D minor, I think it's called.
Strings. It was all strings.
Yeah, I think so. And it's probably a rather low-budget sci-fi movie about what humanity does when the sun is going out.
Yeah, they had to do something to like spark it back into action or something.
Yeah.
Yeah, and the spacecraft that they were on to go do it, there was all kinds of interesting plot twists on the craft, on the ship, going there with the crew. Isn't that correct?
I'm not sure.
Yeah. I don't want to give it away in case anyone wants to watch it.
Yeah. Beautiful music, though.
Oh yeah, Science Bob says he loved the octopods in Arrival. Those are very cool. And it's kind of interesting, too, because those octopod creatures in that movie, they communicate in a way that's completely alien to us. They communicate with an extensive language of symbols that are made out of what looks to us like smoke, but which may be to them their language visualized. And it was interesting how they were trying to determine what was what in there, you know. It was really cool. Was it tetrapods or was it octopods? I don't remember. I think it might have been tetra. No, they didn't have 3 fingers.
Tetra's 4.
That's quadrpods.
That's tetra too.
Tetra's 3. Tetrahedron, you know. That's all right. I don't remember.
Tetra's 4. Trust me.
Okay.
Fantasy agrees. That was a movie with Amy Adams, right?
I don't remember.
She was the linguist that figured out how to talk to him.
Probably that, yeah.
Yeah, Amy Adams, redheaded actress.
Yeah. It was quite good. Solar Crisis, Donald's talking about, and I think that's another one on the same vein of, you know, the sun doing something very bad to us. Izabela says the visual of the language, again with those tetrapods or whatever they were. The visual language was a masterpiece. It was. It was very cool. It had to be as alien as possible, and that certainly was alien. And they were larger than us. They lived in a different atmosphere, and they basically could make and manipulate gravity. Every aspect of that movie was really just a cool, groundbreaking piece of concept that I saw. Because that's probably realistically how it would happen, you know, in that regard, that kind of thing. They're not evolved past the use of bodies, but they're also evolved to the point where they would still want to explore, and, you know, they didn't explore too much without just making assumptions about why they were on the Earth. You know, they were showing up all over the Earth and they were trying to, again, in true Hollywood fashion, here to warn us or save us or some such thing.
The only other movie I can think of offhand I ever saw Amy Adams in was Talladega Nights, The Ballad of Ricky Bobby.
Yes.
Whatever it was.
Yeah.
I know she's been. She was in the at least some of the what's his name? The English guy that played Superman, Man of Steel.
Oh yeah.
He played The Witcher. I'm having a brain lock. I must be turning into a pumpkin.
Yeah. I'm getting tired too, but you know, it's okay. Fantasy, you might have accidentally silenced Science Bob a bit. I don't know why you did that, but I'm sure you'll tell us. All right. Oh, he posted the plot of the movie. Okay, gotcha. Bob, come on now. Don't give things away. All right, we're here at the cave. We got 51 objects, 51 of these, and we're going to just save it again. And I judge how long we're going by how much my butt hurts in this chair. It's actually a very comfortable chair. That tells you. Of course, I did a pretty long workout today, so I'm just a bit on the beat side. Ended up walking doing a 2-mile hike earlier.
You cranked that image up, didn't you? Can you crank it back down a little bit?
Yeah, I can. I can crank it up. I mean, let me distance the mid-level and bring it down.
I see looks like the streaks from that artifact over on the left side are making those lines across the image.
I mean, this here?
Well, I see those lines like I saw last night. Some of them look like they're coming from that thing on the left, yes.
Oh, yeah. It makes a radial set of lines. And I got to remove those later. This is really nice, though. This is coming out nice.
Yeah.
Let's zoom into this. Oh, look at that. That's really pretty. That's the heart of the cave right there. You can see detail in this now, Daryl.
A cave is just a hole on its side.
That's a good one.
That's from Fire Sign Theater a long time ago.
Yeah.
Anybody remember Fire Sign Theater? They did these comedy albums back in the 70s and the 80s.
Do you remember Second City Television? Remember with the little Indian symbol?
Donald knows exactly. Everything you know is wrong. That's really funny. That it reminds me of Bill, New York Skywatcher. It's about a guy running a radio station that talks about aliens and UFOs constantly. And the aliens show up at one point.
Oh, yeah?
Dogs flew spaceships. Aztecs invented the vacation or something like that. Everything you know is wrong. They did another really funny one called Waiting for the Electrician or Someone Like Him. It was a takeoff on Sherlock Holmes.
Mm-hmm.
And Sherlock Holmes' cocaine habit was involved also.
Oh,
Again,
okay.
this was the 70s. Really funny album.
Cosmic Ray, if you notice over here, he asked a question about dark frames. Notice here, Ray, subtract the dark frame automatically. I am doing it. And I'm also applying a flat frame here. I'm doing it. So I am doing a dark frame and a flat frame. If I didn't do a dark frame, there would be a considerably lighter view over here. This artifact here is reduced, believe it or not, by quite a lot because of the flat frame. But unfortunately, different exposure levels, you should have a flat frame for different exposures. And I'm doing, here I'm doing this 25-second shot, or 20-second shot. And my flat frame is for, I think, like a 25-second or something like that, or maybe 30 seconds. So it kind of produces an inverse effect sometimes. All right. Well, we're at 64. We're going to go to 65 on the cave, and then we will be done. JSCO77, I hope you're happy. This is your one more. You asked for it. You got it. Toyota.
Fantasy says no, they were heptapods.
Yeah, that's right. Heptapods.
7.
Did we just get a red one? No, we got a green. Oh, 65. There we go. So we'll save that. And save exactly as seen. Alright, let's see if our annotation will notice this one and be able to identify it. This one it probably should. It's pretty well known. Let's do it. Yeah, there we go. The Cave Nebula right there. Nice. And Hipparchus 113-249. Okay. That way you know what you're looking at. Cool.
Was this the just one more?
Yeah.
Oh, okay.
You wanted to do the elephant's trunk, didn't you?
Read my mind.
Yeah, it's right nearby. Yeah, but I can't do more than that. I'm gonna have to call
It's
it.
fine.
Yeah.
Yeah, we have the whole season ahead of us.
Yeah, we do. All right, folks. Well, I want to thank you guys for joining us. Those images that we've all done tonight will be up online for you if you want to go to skytourlive.org and read the instructions on how to get to them. When the application is up and running online, we will certainly let you know, because we want everybody to have it, so you can actually look and search for yourself and see everything. It'd be updated relatively frequently once it's a live application. All right. So now what I'll do is I'll park the telescope here, and you'll see it go to its home position. So I'll jack this over here, and there you go. So it's coming down. You can see the shadow from the infrared illuminator from the camera that's out here, okay, looking this way, which is this view here. So that view casts a shadow on the wall with the infrared illuminator. I think that's kind of cool. Okay, now what we'll do is we can shut off the telescope, and we're going to shut it off. This is our program there. Okay, telescope is now shut down, and we can shut our roof. And there we go. From 2,600 miles away, across the Rockies, we're shutting the roof of a building out in the middle of the Arizona desert. And there might be a pack rat out there looking up going, what in the heck is that? Well, there we go. All right. Thanks, folks, for coming. We enjoyed your company a great deal. And hopefully you guys will join us again for our next clear night, when we'll do things like the elephant's trunk and other planetary nebulae that are coming up as well. And yes, we'll get to the helix. Okay, we'll do that, I promise. So it's great to see you guys. I hope you have a good evening, and we will talk to you on the flip side.
Good night, everybody.
Good night, everyone.